Hello, in this lesson, I want you to factor binomials that are a difference of squares. I want you to factor trinomials that are perfect squares. Some vocabulary we're going to take a look at is difference of two squares and perfect square trinomial. We're going to start here with difference of two squares. We can factor this by using all our rules. Nothing has changed. We're not really actually doing anything new. Except what we're trying to do is make you realize there's a shortcut sometimes, because like you're on your ACT, they'll give you 60 math questions in 60 minutes, and they like to throw these questions on there because if you understand how to do it, you answer the question in about 2 seconds and you move on. If you don't understand how to do it, then you spend a lot of time on it and you run out of time on your test. First off, the only time you can factor a binomial, two terms, is if the first term is a perfect square and the second term is a perfect square. If that's the case, then it's going to be the square root of the first term plus the square root of the second term times the square root of the first term minus the square root of the second term. We've done this before. It's just backwards. So if I look at x squared minus 25, x squared is a perfect square, 25 is a perfect square. The square root of x squared is x. The square root of 25 is 5. So I'll say x plus 5 times x minus 5. And once again, the order doesn't matter. I look at t squared minus 64. The first term is a perfect square. The last term is a perfect square. So my first term, the square root of my first term is t. The square root of my second term is 8. So it's t plus 8 and t minus 8. So what happens on our directions here? It says determine whether each polynomial is a difference of squares. If it is, we're going to factor it. Well, kind of like I said before, I think what we'll try to do is answer that question. So I look at my first term. Is it a perfect square? 16 is a perfect square because 4 times 4 is 16. 9 is a perfect square because 3 times 3 is 9. I got a minus sign between them. So yes, this is a difference of squares. Let's factor it. I'm going to make two parentheses. The square root of 16h squared is 4h. So that goes in the front. The square root of 9a squared is 3a. I'll put a plus and a minus. The reason it's plus and minus is because it has to multiply to a negative, so one's positive, one's negative, and we're done. That's it. That's the difference of squares. Let's take a look at our second example. My first term is a perfect square because the square root of 121 is 11. C to the fourth is a perfect square because it's even. 25 is a perfect square, but notice what happens. We have an odd exponent here. That's not a perfect square. So we can't factor this. We're going to say no. And why? Because d cubed is not a perfect square. They must be, both terms must be perfect squares in order to use the shortcut rule. Now, perfect square trinomials. First off, notice difference of squares with a binomial. Now, this trinomial, that really isn't much different than what we've done. So what happens is, notice, you get a trinomial, and you say, hey, is the first term a perfect square? Is the last term a perfect square? Is the middle term twice those two multiplied together, because we get the twice part from when we multiply it. And then if the middle term is minus, that's a perfect square, but it's a minus sign. So it'll be a minus b squared. So that's all we notice. So on this one, we're going to approach it, I think, a tad bit differently. Rather than determining if it's a perfect square trinomial to start with, I'm going to see if I can factor it using my perfect square trinomial rules. If I can, I'm done. And if I can't, then I know it's not a perfect square trinomial. So I look at my first term. Example 3. 4y squared, that's a perfect square, isn't it? 9, that's a perfect square. So I think this is a perfect square. I'm guessing right now. So I'm going to go parentheses. The square root of 4y squared is 2y. My middle term is plus. And the square root of 9 is 3. Now, is that true? Well, let's see here. If I take 2y times 3, I get 6y. If I double that, I get 12y. So yes, this does. We can show this a little bit more work by actually multiplying it out. If I take 2y plus 3 squared, which it means you take it times itself, times 2y plus 3. If I do my double distribute, I get 4y squared plus 6y plus 6y plus 9. So I get 4y squared plus 12y plus 9. That checks. So my answer is 2y plus 3, the quantity squared. Let's take a look at example 4 here. If I look at example 4, my first term is a perfect square because this 9 is 3 times 3. X squared, my last term is a perfect square, so I'm guessing this is a perfect square. So I'm going to say parentheses. I'm going to go, the square root of 9x squared is 3x minus. The square root of 4 is 2. Then I'm going to square that. Now, if I take my terms, multiply them together, and double it, because there's 2 parentheses, 3 times negative 2 is negative 6. I double that, I'm supposed to get negative 12. Uh-oh. So no, this is not a perfect square. Since it's not a perfect square, I don't have to worry about factoring it for these types of problems. That's all you would have to do on that.